The reason we would be using these techniques is because we're trying to integrate some trig function or a fraction, and so we're trying to make integration possible, but we're only trying to do this, and this is important, if it's not already possible. So for example, don't forget fractions might be the derivative on the top, and you know how to do that. That's just ln of the bottom. Or you might have something that you could do a little bit of trig on and it turns into something you can integrate. Now the standard ones that you need to learn for trigonometry is sine squared, cos squared, tan squared, cot squared. Okay, these 4 squareds, the other squareds you already know how to do. So sec squared you can integrate already. And what's the other one that's missing? Cosec squared. You can already integrate both of those because you know what was differentiated to get them. So these are the other 4 squareds. And you simply replace sine squared with a half 1 minus cos, but double the angle. You replace cos squared with a half 1 plus, difference is the minus and the plus there, double the angle. Don't forget to double the angle. Tan squared you replace with sec squared minus 1, cot squared you replace with cosec squared minus 1. You can also integrate anything like this using the formulas in the formula book. I'm not going to write them out because they're really long, but so look, if you get sine of something, cos of something, and the angles don't match, or sine sine or cos cos, then look up in the formula book. There's formulas that you can use, and then you can go ahead and integrate. Now, I'm not going to do these as demonstrations because that is literally all you do. You replace that with that, you replace that with that, you replace that with that, that with that. These you replace with the formulas out of the book, and then you go ahead and do normal integration. What I'm going to do is show you these fractions and show you that things that look really similar don't necessarily have the same techniques for solving them. So first thing with a fraction to remember is, same as with what I was saying here, can you already integrate it? So is it ln, because the derivative of the bottom is on the top? Or can you just factorise the top and then cancel off a factor? Or could you use the v method? So you've got like 2 things, this one and this one on top of this one, and you can break it into 2 fractions. Maybe you can do that. If not, if it is legitimately a fraction that you can't yet integrate, then we've got 2 techniques. We've got algebraic division and partial fractions. Now you use the partial fractions if the bottom is heavier and factorizable or factorized. So the bottom is heavy, the bottom's a quadratic, which is heavier than a linear. So the bottom is heavy and the bottom is factorized. That means we're going to use partial fractions. Now with this one, the bottom is not heavy, it's the same. So this one, like neither of them are heavier. This one, the top is heavier because the top is a quadratic. So the top is heavy. In this case, neither one is heavy, and we just say still that we're going to use the algebraic division. So the top is, well, it's not heavy, is it? It's the same. So if the top is heavy or the same compared with the bottom, we're going to use algebraic division. Let's have a go. So I'm going to use the method of algebraic division that I've shown you in the videos, and that is that we're going to take the coefficients of the top, which is that I've got 4x squareds, no x's, and then the number 1, and then create this little coordinate grid thing. What x would make that 0? Minus 4/3 goes here, and then we start by just putting that 4 down there. Multiply these together, minus 16 over 3. Add these 2 up. Multiply these 2 together. Add these 2 up. Now, what has popped out here is the remainder. What has popped out here is the quotient, but not quite, because if you look, there was a coefficient of 3 on that 3x plus 4, the thing I'm dividing by. So if this had just been x add 4, then that would be the quotient. But what I'm going to have to do is divide it by 3 because there's a 3 here in front of the x. So it will be the quotient once I've divided it by 3, which is pretty easy. Yeah, that becomes 4/3, that becomes minus 16 over 9. That means that my integral, this thing here, can be written like this. 4 x's, it goes down a power from the x squared, 4 x's, well 4/3 because I have to divide it by 3, minus 16 over 9, because I've got to divide it by 3. That's the quotient. There's the quotient. And a remainder of 73 over 9 still over the thing I'm dividing by 3x plus 4. It would be nicer to times top and bottom of this by 9, to be honest. So there's your quotient. and there's your remainder. And what we've done is to rewrite this expression like this, and now we can go ahead and integrate, can't we? Because we know what the integral of this is, raise the power to 2, divide by 2. This one, just stick an x in front of it. This is all first year stuff. And then this one is going to be ln, so it'll have a 73 over 9 at the front, then it'll be ln of 3x plus 4, but then we've got to compensate for that 3, so there'll be a divide by 3, blah, blah. That's all stuff we've done in other videos. Right, let's do the same thing here a bit faster. So we've got on the top 4 x's and then a 1. And then on the, we make our little grid. What makes the bottom 0? Minus 4/3. Write the 4 down here. Multiply these together and write it here. Add them up. That should be a 3. Just realised. Add them up. Minus 13 over 3. So this is going to be the quotient when it's divided by 3. 3 because it's the coefficient of x on the bottom. And this is the remainder. And that means that this expression here can be written like this. 4/3, because I've gone down a power. It was just an x, so I've gone down a power just to numbers. And then also the remainder on top of 3x, add 4. There's the quotient. And, well, actually I wrote remainder there like it's the whole remainder. Obviously that is the remainder, that number there. That bit is the remainder. And now we can integrate. So this is going to become 4/3 x, and then this one will be ln. It'll have a minus 13 over 3 at the beginning. It would be nicer to put this plus and minus together to make a minus and times top and bottom of this by 3, but you don't have to. And it'll be ln of 3x add 4, but then you'll have to divide by 3. And then that'll all work out. So what are the common mistakes that are going to happen when you're doing this? Okay, very, very common mistake is if you're using these formulae here for sine squared and cos squared, then the plus and the minus the wrong way round. Obviously, I mean like this, they're exactly the same, but that one's minus and that one's plus, so getting them the wrong way round. And more common, not doubling the angle. So that A there has to get doubled here. The next most common mistake is not checking partial fractions or algebraic division. So you use algebraic division or partial fractions, and then on we go like I just said just now. Now, I'm going to check at the end. It's easy to check an integral if you've got limits, because you can just type it in. If you haven't got limits, it's really hard to check. So limits, you can use your calculator to literally just integrate it using the button we've seen lots of times. And if there's no limits, then you can't check it. Now that makes it even more important that you check your partial fractions or your algebraic division. It's easy to check, isn't it? All we're going to do is we're going to get our calculators. So for example, this one. Fraction, I'm going to use x is 2.5. 4 lots of 2.5 squared, add 1, over 3 lots of 2.5, add 4, is that number there. Now I think that this expression here that I'm going to integrate is identical to this expression. So if I put 2.5 in this expression, it should be the same. What have we got? 4/3. Okay, moment of truth. If I'm right, if this expression is the same as this expression, if I did my algebraic division correctly, this will come out to be 2.26086965, blah, blah. Hooray! Okay, so I now know that provided I get my integration right, I'm going to get all the accuracy marks. Whereas if you have made a slip here, then when you integrate, you can integrate correctly, but you're going to lose all the accuracy marks. Right, last but not least, partial fractions. So what we're going to do, we're going to work out what shape this was originally. 3x add 4 squared. So it will have been something over 3x add 4, add something else over 3x add 4 squared. Go back to the partial fractions video if you're not sure. Times both sides by the denominator. And then choose whether to use substitution or equating coefficients. I'd probably use, I don't know, both easy here, aren't they? I don't know what I would use. Anyway, let's use subbing in. When x is 0, what would you get? 1 is 4a plus b. Okay, when x is 1, what do you get? You can sub in whatever you like. So you'd get 5 is 7a plus b, and then you could do simultaneous equations to get the a, which comes out to be 4/3, and the b, which comes out to be minus 13/3. So the integral that we were dealing with here is actually the integral of a, 4/3. It's nicer to times top and bottom by 3 and write it like that. Plus b is minus 13/3, 3x add 4 squared. Now, final point for this video, which has been a very long one, but it's a very important one, is the difference between integrating 1 over x plus 1 and 1 over x plus 1 squared. Now, a lot of students go ahead and integrate this one, ln, and then they think this one is also ln because it's 1 over. Now, the integral of 1 over something linear is ln, but the integral of 1 over something not linear, like a squared function, is not. So this is really important. It happens a lot when you do these partial fractions because you end up with one like that and one like that. That one has come from ln. That one has come from 3x plus 4 to the power of minus 1. So very, very careful with that common mistake there.